Stability of slopes for dam excavation by slope mass rating in the Pear Hydroelectric Project. Abstract dam is an important element in all river valley projects, and excavation of both banks of the river, where the dam is abutted, is a very important consideration for the total cost of the project. Thus, the stability analysis of the side slopes of the rock mass is a very important exercise, for a feasible hydroelectric power project. The study area lies in the Papunpare district of Arunachal Pradesh, India, which is represented by Upper Siwalik subgroup of the Sub-Himalayan range. In this paper, the stability of rock slopes for a stable excavation for dam construction is analyzed with the help of slope mass rating, SMR, by using basic rock mass rating. Support measures, wherever required, has also been recommended based on SMR. The satisfactory performance of the excavated slopes at the dam site of Pear HEP project establishes that SMR method can be used with confidence for rock slope stability analysis. Keywords: SMR, RMR basic, adjustment factors, stability. Introduction. Concrete gravity dam of a hydroelectric power project is abutted to the fresh rocks on both banks of the river. A stable, yet the most economical slope, needs to be designed for the purpose. In this paper, Slope Mass Rating System, Ramana, 1985, as in 1 is used to study the stability of the rock slopes for abutting the dam of the Pear HEP project at Papunpare district of Arunachal Pradesh. The study area lies within the Upper Siwalik subgroup of the Sub-Himalayan range and are characterized by soft tertiary sedimentary sandstone/siltstone. 4 drill holes, namely, .2, 3, 4 and 5, drilled by NIPCO Limited along the dam axis, exhibits repetitive sequence of coarse to fine-grained, grayish-colored, soft, friable, moderately fresh sandstone, pebble-impregnated sandstone, sand rock and pebble beds, on either banks. Geology of the dam site, as mapped by geologists of NIPCO Limited, are presented in the following subsection. 2. Geology of dam site. The left and right rocky abutment was identified with 3 sets of joint oriented in different directions. The dip/strike of the joint sets are given in the Table I. Table I: dip/strike of joint sets. Left abutment. Right abutment. 3. Rock mass classification. In a river valley project, excavation of a dam requires the modified rock slopes to be stable. The improper excavation methods on natural slope conditions and modification of cut slopes can develop new cracks which may lead to instability of the rock slope. Therefore, the preliminary approach of a dam excavation should include the understanding of the geological and geomechanical parameters to prevent slope failure during and after excavation. For various engineering designs and stability analysis, rock mass classification systems form the cornerstone of empirical design approach and are extensively implemented in rock engineering. Rock mass classifications have been recently employed in underground constructions, tunneling and in mining projects. Barton 1974, 1988, Wieniawski 1989, Lobsker 1990, as in 234. A rock mass is characterized by comparing the values obtained from visual inspection or by simple tests with some standard sets of descriptions and values for some specific parameters. Thus, with the help of standard qualitative data and guidelines, rock masses described by different geologists and engineers at different locations can be compared and analyzed. A rock mass rating system. This classification system, developed by Wieniawski in 1973, 5, can be applied to a given rock mass that is divided into a number of geological structural regions where each region represents separate geological structural unit. Generally, the boundary of the units coincides with a change in the rock type or with structural features such as fault. The following are the 6 representing parameters, given by Wieniawski in 1989, which are determined for each unit. 1. Uniaxial compressive strength, UCS, of intact rock material. 2. Rock quality designation, RQD. 3. Joint or discontinuity spacing. 4. Joint condition. 5. Groundwater condition. 6. Joint orientation. All the above mentioned parameters can be obtained from field and can also be measured from borehole data. The ratings of these 6 parameters are summarized and the RMR value is obtained. As the dam block is divided into 9 blocks, the basic RMR is derived for each of the blocks. A. Uniaxial compressive strength of intact rock material. Table 2 shows the rating of the parameter uniaxial compressive strength, which is calculated using the relation of principal stresses. C. Discontinuity spacing. There are many set of discontinuities present in different dam blocks, some ranging from very closely spaced to moderately spaced while some are randomly spaced. Ratings are given accordingly for each discontinuity set occurring on the rock mass, Table 4. D. Discontinuity condition. This parameter includes continuity, aperture, weathering of the planes of weakness or the wall rock, roughness of discontinuity surfaces and infilling materials present in the discontinuities. From the geology obtained from dam sites, the ratings for each of the conditions have been calculated for each dam blocks and are found to fall under the range of 19 to 25. This implies that the rock mass is of mixed quality conditions, as both good and poor quality prevails. E. Groundwater condition. The general hydraulic condition derived from this site varies from moist to dripping. Table 4 shows the computation of the corresponding values of basic RMR of the 3 joint sets from the ratings of the parameters. The basic RMR values are computed for dam block 1 and 9, as it falls in left and right abutment of the dam site respectively. The above RMR basic values obtained can be used to calculate the slope mass rating values, which will help to predict the stability of the rock slope. B. Slope mass rating, SMR, system. Slope mass rating system has become the most extensively used classification system for rock slopes. The SMR system is the extension of the basic rock mass rating along with 4 adjustment factors that take into account the geometrical relationship between the rock slope face and discontinuity affecting rock mass, factors F1 to F3, as well as the excavation method used, F4. Romana, 1985, derived SMR system for the purpose of assessment of rock slope stability, from the studies of natural and cut slopes along the roads. It is obtained using the following expression. SMR equals RMRB plus, F1, F2, F3, plus F4, 1. Where RMRB is the basic RMR obtained from Wieniawski's rock mass classification system without any correction. F1 depends upon the parallelism between discontinuity, AJ, and the plunge direction of line of intersection, AI in case of wedge failure, and slope dip direction. It ranges from 0.15 to 1.0. Initially the value of F1 was established and was found approximately equal to 1 Sena, 2, where A represents the angle between slope strike and joint strike. F2 depends on the discontinuity dip, SSJ, in the case of planar failure, and SSI, or plunge, of the intersection line in wedge failure. Its value also varies from 0.15 to 1.0. For toppling failure, F2 is 1.0. Empirically, F2 equals tan psi. F3 depends on the relationship between slope dip, SSS, and discontinuity dip, SSJ, for toppling or planar failure cases, or the plunge of line of intersection, SSI, wedge failure case. F4 is a correction factor that depends on the excavation method used. For the evaluation of the adjustment factors, some dip angles of the slope face are considered, and with the help of dip/strike of the discontinuities all the factors are calculated for the rock masses. The strike of the dam axis on left bank is north 74 degrees east, so the slope strike for the left abutment is found to be north 164 degrees, and strike of the dam axis on right bank is south 74 degrees west, and thus the slope strike for right abutment is found to be north 344 degrees. According to the formula proposed by Romana, 1985, all the adjustment factors have been calculated. 1. Adjustment factor F1, using the formula F1 equals AJ as, where AJ is the joint strike and as is the slope strike, it has been observed that for slope strike north 164 degrees on the left bank and north 344 degrees on the right bank of Pear River, orientation is very favorable with respect to the strikes of the joint sets in most of the considered cases, except for joint strike ranging from north 150 degrees to north 180 degrees present on the left rocky abutment, with slope strike north 164 degrees, which refers to fair condition. This represents that overall both the slopes are stable with respect to adjustment factor F1. 2. Adjustment factor F2, as F2 depends on the joint dip angle, it has been observed that only for joint dip 28 degrees and 32 degrees the factor F2 comes out to be favorable and fair respectively. For other joint dips greater than 45 degrees, F2 represents very unfavorable condition. This refers that the slope may undergo planar failure. 3. Adjustment factor F3, as the adjustment factor F3 refers to the relationship between joint dip and slope dip, the values of F3 are obtained for various slope dip with respect to the three joint sets present on both the abutments. For the left abutment, a number of slope dip, SSS, are considered ranging from 45 degrees up to 75 degrees, and F3 is calculated for each joint sets as shown in Table V. Similarly, in the right abutment certain slope dips are considered ranging for 45 degree-75 degree, and F3 is calculated for each of the joint sets as shown in Table 6. 4. Adjustment factor F4, this adjustment factor is related to the method of excavation, which includes natural slope, or the cut slope excavated by pre-splitting, smooth blasting, normal blasting, pour blasting and mechanical excavation. As per the information gathered from the agency, it has been known that mainly pre-splitting is used while excavating the slopes. Value of the adjustment factor F4 for pre-splitting is plus 10 as proposed by Romana, 1985. 5. Calculation of slope mass rating. The slope mass ratings are calculated for the rocky abutments situated on the either banks of the River Pear where joint sets and bedding planes are present, using the formula as in 1. For the ease of the calculation, only the extreme values of the range of dip and strike of a joint set has been considered, for which SMR values are obtained, and rest of the angles under that range are considered to fall under that particular range of SMR. A. SMR for left abutment. Here, all the SMR values for the rock mass present on the left bank of River Pear have been calculated, and the failure modes have been determined for each of the joint sets with respect to the considered slope dip angles as shown in Table V. B. SMR for right abutment. Similarly, all the SMR values for the rock mass present on the right bank of River Pear have been calculated, and the failure modes have been determined for each of the joint sets as in Table 6. Thus, from the above table it has been observed that the rock mass is partially stable with respect to plane failure except for joint dip 45 degrees with joint strike ranging from north 150 degrees to north 180 degrees, which indicates that the left rocky abutment is completely unstable due to the presence of this joint. Factor F3 comes out to be very unfavorable for joint dip 45 degrees and also for 32 degrees, having joint strike north 195 degrees for all the considered slope dip angles. While, as the slope dip increases, the rating of F3 decreases and thus in turn increases the instability of the rock slope. When we consider toppling mode of failure, the rock mass comes out to be favorable. In Table 7 the stability criteria of the left rocky abutment along with the failure probability is given with respect to the dip/strike of the discontinuity sets present in the rock mass. SMR for the right rocky abutment shows that the rock mass is comparatively better than the left rock mass because of the orientation of the discontinuities, for which the ratings of adjustment factors F1 and F2 came out to be good, while for factor F3, ratings are decreased as the slope dip has been increased. As a whole, the right abutment mostly lies in the partially stable category, and for each of the three joint sets present in the rock mass in relation to the considered slope dip of 55 degrees and has been observed to be fair. In Table 8 the stability criteria of the right rocky abutment along with the failure probability is given with respect to the dip/strike of the discontinuity sets present in the rock mass. For observation. The rocky abutment present in the left bank of River Pier consists of three set of joints which are oriented in both favorable and unfavorable orientations. Joint set 2 is found to be the most critical joint sets, having dip angle ranging from 45 degrees to 75 degrees. Joints with dip of 45 degrees produce completely unstable slopes, which require re-excavation, even for slopes with slope dip 45 degrees. However, joints with dip 75 degrees have SMR value above 40 for slope dip up to 70 degrees and is partially stable, which can be made stable with corrective support measures in the form of systematic bolting/anchors or systematic shotcrete, etc. In the field, it is found that with these measures rock slopes are stable for slope dip up to about 69 degrees. Thus, it may be concluded that for joint set 2 in the left abutment, predominant joint dip is 70 degrees to 75 degrees. Rock in the right bank of River Pier is better compared to the right bank and falls under partially stable category with 40% failure probability. Conclusion. The pier rock mass is found to be characterized by three joint sets both at the right and the left bank at the proposed dam site of Pier Hydroelectric Power Project. In the left bank, during geological mapping, it was observed that joint set 2 has joint dip ranging from 45 degrees to 75 degrees. Joints having 45 degrees joint dip renders the rock slopes with 45 degrees slope dip and steeper completely unstable. However, at the site it has been found that rock slopes up to about 70 degrees stand, albeit with certain support measures, but are not completely unstable. This may be because the predominant joint dips of joint set 2 are close to 75 degrees. Present study shows that the right rocky abutment is partially stable, having 40% failure probability, thus can be regarded as normal rock slopes. Left rocky abutment is found to be completely unstable with 90% failure probability. Acknowledgement. This work is the result of a research project sponsored by NIPCO Ltd. We sincerely acknowledge NIPCO Limited for providing us the various geological as well as geotechnical data of pier rock mass, which was necessary for carrying out the present work.